So today I'm gonna start off by reviewing what we've learned about calculating confidence intervals, right? And the reason why we're so interested in confidence intervals is because we're almost always dealing with a sample from a population. We never seem to know what mu, the population mean, is equal to. We're never going to know that in most cases. Even after we do a study, we're not going to know what it is. However, we can't stop there. We still have to do what we have to do. So we have a large population and we want to estimate what mu is. We take a sample. That sample can have can be small, it can be large, it could be very large, right? We have all sorts of different, depending on what our resources are, what we're trying to show. We might take different sample sizes, but we almost never get an opportunity to sample the entire population, right? Say something like n is infinity, for instance, for everybody, for instance. Okay, we never get to do that. So we need a way to tell when we take a sample and we calculate the mean of that sample, we needed a way to describe how accurately we know that sample reflects what the mean of that population really is. Well, that's kind of hard to do because if you take a single sample, all you got is the mean of that population, right? You can't really compare it directly to the population. But what we can do is we can look at the variability of our sample. So like in other words, we can say to ourselves, you know, if the numbers look like this, 9, 10, 11, 10, 9, not much variability in the individuals that we picked from that population in our random sample. But if we look at another sample and they come out 2, 7, 15, 20, 3, where there's a lot more variability, that gives us a higher level of uncertainty about how close our mean is to the actual population. So the way we're going to take advantage of that is instead of trying to say, you know, that we know the mean within 3% or 10%, we're actually going to set up something called a confidence interval. Okay, and that confidence interval is going to tell us based on the variability of our sample. Okay, and you may remember that in some of the early examples I gave you, I told you, let's make believe we know the population standard deviation. Because if we know the population standard deviation, we have a really good handle on the variability and how a sample is going to perform in that situation. But a lot of times we don't know that either. A lot of times we're dependent on estimating the variability of the population from the variability of the sample as well. So we wind up not knowing mu, not knowing sigma, right? And we have to estimate them from X bar and from our variability, which is going to be our standard deviation of the sample itself. And everything we know about that population and how well we know it is going to be based on those things and the sample size. Okay, so we established something called confidence intervals. And the reason why we could do this is because we learned something about the essential limit theorem that helped us understand what the behavior of samples from a population will look like if we do it over and over and over again. What that behavior or those sample means would look like, given that we have an estimate of the variability of the population and whether we really know it for sure or we're going to base it on standard deviation, and what the size of the sample is, right? Those things help us figure out what the behavior of samples from a population are. So we can use the central limit theorem to tell us, well, okay, let's say X bar we find out is equal to 100, right? If we know what the standard deviation is, we can use that. If we know sigma or the standard deviation, we can use that to figure out, given the sample of the size that we're working with, whatever it happens to be, let's say it's equal to 100. Okay, given that sample size, we can figure out what variability we would expect in samples that are repeated over and over and over again, based on the variability of the sample itself. We know that we call that the standard error, right? And that's equal to sigma or the standard deviation, whichever one we have, over the square root of the sample size. So that standard error tells us a lot about how likely it is that this sample of 100 is close to or far away from the mean based on what the behavior samples are. So we've said to ourselves, okay, we're going to establish that our estimate of the variability here and where we're starting with from our sample is going to be X bar plus or minus some value like 2 standard deviations, right? Some distance on the normal distribution that is the sample means, times the standard error, the variability from the samples that we would be taking. This is the variability of the sample means times 2 for 2 standard deviations. Well, 2 is really an estimate, right? It's really 1.96 that we're usually interested in, right? So this gives us an idea. For instance, in this case, let's say that the standard deviation was equal to 20 and the sample size is equal to 10. This would be equal to 2. 20 divided by square root of 110, that would be equal to 2. So this would be roughly 100 plus or minus 2 times the standard error, which is 2, right? So it'd be roughly 100 plus or minus 4, or 96 to 104. So from that simple example, we can predict that in this sample, based on the sample size, based on the standard deviation or sigma, and based on the fact that we're willing to accept, that we're willing to be satisfied with 95% confidence, right? That's where the 1.96 came, 95% confidence. Based on that, we can predict that with 95% certainty, the true population mean is going to be between 96 and 104. We're never going to know if we're right, right? All we're going to know is that that's our level of confidence. But the mean, the true mean, is always going to escape us. We're never going to know that unless we go back and sample everyone. Okay, so let's take a look at the various ways that we might run, the various different situations where we might run into this. I'm going to start a new page. Okay, and this is all preparatory to what we're going to talk about today, which is our first introduction to real hypothesis testing in biostatistics. Okay, so let's take a look at some of the situations we might run into. Well, one situation is we measure X bar, we take our sample, measure X bar, we know sigma, we know the population standard deviation. Not this version is not going to happen very often, right? We know sigma and we know our sample size. Well, in that case, we can calculate our standard error because it's going to be equal to sigma over the square root of the sample size. So these are the things that we know when we're working with a situation where we know what the population standard deviation is. And we can use that to predict a confidence interval for the population mean. That's going to be a rare situation. That's the situation that we kind of set up for us because we want to practice this without introducing another uncertainty that comes up now. Now, in real life, we take a sample. We're going to get a mean from that sample, that random sample of individuals in that population. And we're not going to know population standard deviation. But, you know, the variability of the people we chose using our sample is probably going to be the same variability as the population, right? In other words, if the population variability is somewhere between 80 and 120, then our sample is probably going to be in that range also. So we're going to use the standard deviation to approximate sigma, right? That's going to be our estimate of sigma. And then I'm going to know my sample size and my standard error. Well, I don't know sigma, so I have to calculate it based on my approximation of sigma, which is that my standard deviation divided by the square root of n, right? So what's the difference here? The difference here is that we've introduced an extra element of uncertainty since we don't know what sigma is, and we have to rely on the standard deviation to substitute for it. So in this case, we have to make an accommodation for it. So I'm going to do 2 examples right now that in one situation, I'm going to tell you we know sigma, right? And in the other situation, I'm going to tell you that we don't know what sigma is. Okay, so let's say that our mean is 100. Let's say that sigma, the standard deviation of our population, is equal to 10. And let's say our sample size is equal to 25. Well, what is our standard error? Our standard error is sigma which is 10, divided by the square root of 25, which is 5, and that's equal to 2. Okay, so if we wanted to calculate our confidence interval, we would say in this situation, x bar plus or minus 1.96 times our standard error. Okay, what's that going to be equal to? It's going to be equal to 100 plus or minus 1.96. You guys remember where I got the 1.96, right? It's it's basically about 2 standard deviations to the left, 2 standard deviations to the right, and that represents 95% of the outcomes I would expect. In this case, it's 95% of the means that I would expect taking a sample of size 25, and my standard error is 2. That's the standard deviation, basically, of the sample means, right? Not the population. Population standard deviation was 10. This is how we expect the variability of the sample means of that size to look. Okay, so we would effectively wind up with, what does this really wind up being? 100 plus or minus, for you guys that are watching over here, it's better if you look on the screen because I know once I get down to the bottom there, it's tough, right? 100 plus or minus, this is going to be 3.92. Right there, 3.92. Okay, and if I add and subtract that, that comes out to be, on the high end, that comes out to be 103.92, and on the low end, it comes out to be 96.08, I think. The 100 was, I gave that to you. That's the sample mean. That's X bar. Okay, that was X bar. Okay, that, in other words, I took my sample. I took a sample of 25 randomly selected people. The mean came out to be 100. I knew the population standard deviation was 10, and I calculated my standard error for repeated samples of size 25, given that the standard deviation of 5. That standard error is going to be sigma over the square root of n. In this case, it's going to be 2, right? So I have use that to calculate my margin of error, right? That's called my margin of error. And it comes out to be 96.08 to 103.92. And since I know what sigma is, even though this is a small sample size, even though I know what sigma is, I can say that with 95% certainty, then I know that the true mean is going to be between those two numbers. I don't really know it's between those two numbers. I know it with 95% certainty, not 100% certainty. Just to make things a little more confusing and introduce something else, I also knew that if I wanted to be 99% certain, this had to be wider. So I would use 2.58, right? And that 2.58 comes from our Z table, because that's how many standard errors apart you have to be 99% certain. In other words, 0.5% on one end, 0.5% on the other end. And if I didn't need to be that certain, in other words, I was perfectly willing to say I only need to be 90% sure, we can look at a narrower range, and then for 90% certainty, we would use the number 1.64 instead of 1.96. Okay, so what justified me doing this? What justified me doing this was that we knew the population standard deviation. And even though it's a small sample, I know how samples behave. This is the way samples behave. And since I know what sigma is, I can predict this, pretty accurately. Okay, so now, on the other hand, let's say I tell you we take a sample of the same size 25, and the standard deviation of the sample, we get really lucky, and it happens to be the same as the standard deviation of the population, turns out to be 10. It's going to be an approximation. It might come out to be 9, 11, 9.5, 11.5, but I'm going to call it 10 for our purposes. And the mean comes out to be 100. Okay, now in this case, when I calculate my standard error, I don't know what sigma is. So I have to use an estimate for sigma. In this case, I'm going to call it 10, right? Could have been 9, could have been 11. I'm just going to use 10 because it's going to come out a nice even number. Divided by the square root of the sample size, which is 5, right? 25.5. Okay, and that's going to be equal to 2. Same as we had before. But there's a problem here. And the problem now is if I say X bar, if I build my confidence interval, X bar plus or minus 1.96, I'm not going to write that in there, times my standard error, I'm going to get the same variability, the same width of my confidence interval as I got when I actually calculated my standard deviation when I actually knew what the standard deviation of the population was, knew what sigma was. Okay, that's a problem because I know that I don't know this, I don't know the behavior of samples from this population as well as I did over here because I don't know the true population standard deviation. I have more uncertainty here. So to make up for that uncertainty and still you say it's a 95% confidence interval, I have to adjust the width of my confidence interval, right? And the way that I do that is instead of using Z, the Z table, to decide that I multiply by 1.96, because that's the width that I need, right? I'm going to use the T value, the T table value for a sample of that size. Okay, I'm going to call that T. I'm going to call that alpha equals 0.05. Sometimes you'll see it written as alpha over 2 equals 0.025. Don't worry about that right now. I just put that there so if you see it, that you won't freak out. But alpha is a type of error. Alpha error is the kind of error where you say that there's a difference between two groups when there really isn't a difference. In other words, that's our acceptable level of error. So now, in other words here, alpha is equal to 0.05 is the same thing as saying we're 95% sure we're right. Okay, we want to be 95% certain we're right, which means that our alpha is equal to 0.05. We have a 5% chance of being wrong. But I just wanted to introduce that idea of the alpha error right now before we really get a chance to discuss it in more detail. So I need to know what this T value is. And that T value is related to the sample size. The bigger the sample size is, the more confident that we have a good handle on sigma by using the sample standard deviation. So that T value starts out a very large number and gets closer and closer and closer to 1.96, which is what we would use if we had sampled the entire population for the standard deviation. So it starts out a big number, as the sample size gets bigger, gets closer and closer to 1.96. But it only reaches 1.96 when we finally sample the entire population. Let's take a look at the T table. Okay. Yes.
So can you repeat again, when do we use the T table as opposed to?
I'm going to be spending the next half hour on when we use the T table. So we're getting to that. Okay. Okay, you don't have to worry about that. We're going to be discussing that a lot. That's going to be 90% of what we're doing here today. And we're going to apply it another way too. We're going to have an interesting new way to apply it that we're going to learn today too. Okay, so let me get to the T table. You should have a copy of this on Blackboard as well. You have a Z table and a T table available to you in this week's material. So I'm going to go to the T table. Now you can use the one in the book. It's going to look exactly the same. I just like using this one for another text. Okay, so first of all, for technical reasons, we'll explain this a little bit more later on. The T table is laid out in a manner where it lists the values of T by degrees of freedom instead of sample size. And degrees of freedom are just the sample size minus 1, n minus 1. So we go down to a sample size of 25, which is represented by 24 degrees of freedom. And the problem here is that for every different sample size, remember we had a normal distribution, right? We had the 0 in the middle, the standard normal distribution 0 in the middle, and standard deviation was 1, and we use that to calculate the areas that go into the table, and we get a nice big table based on that standard normal distribution. Well, the problem is that you need a new distribution and a new table for every sample size. So if we were working with samples up to size 100, kind of blurs out, it gets weird there. Okay, if sample size 100, make believe it does go down to 100. Okay, if we go to sample size 100, we need 100 different tables, like the Z table, one for every different sample size. So, but the thing here is that we don't really, we did a lot of exercises up till now interpreting the normal distribution, but in practice, when we're really doing things like calculating confidence intervals, deciding whether to reject hypotheses and stuff like that. We're never really looking for what happens at 3% or 11% or whatever. We're always looking at what happens. What do we need to know to be 95% certain, to be 99% certain, to be 90% certain? So rather than worry about all that, what this table does is it summarizes only the critical values that you need to know for T to have different levels of uncertainty. So if you wanted to be 89% certain, you're not going to get it from this table, right? You're only going to get, for our purposes, 95, 99, and 90 is really what we're interested in, almost always, right? So, and almost, I hate to say use another percentage here, but most frequently, by far most frequently, we're interested in 95% confidence. In other words, being having less than a 5% chance of being wrong when we voice our conclusion. Okay, so if you look over here, we see 95% confidence. It also says T 0.025. Well, that's 0.025, 95%. That indicates to you that they're only considering one tail, the high end or the low end, right? Actually, you're talking about the high end of the sample distribution, right? And they're saying that's 2.5% chance that you would be wrong at the high end, but there's also the left tail, which they don't mention there. That's at alpha over 2. Alpha is 5%, chance of being wrong 5%, so alpha over 2. So that's the way that's the nomenclature they use to describe alpha is equal to 5%. Okay, and if you're a statistician, this is the kind of language that you use. But we know that that really represents 5% chance of being wrong, because only accounts for the right tail. You also have to remember that you have to also include the left tail, so you double that for the level of error you're really dealing with, and that means you're 95% confident. And if I go down this list, notice that if my sample size is 11, that would mean 10 degrees of freedom. In order to be 95% certain, the width of my confidence interval has to be 2.228 standard errors. Well, if I go to 25, sample size of 25, we use 24, it has to be 2.064 standard errors apart. That's the number I'm going to use to multiply my standard error to calculate my confidence interval. If I go to an infinite sample size, it's 1.96. That's the z-table. That's what the z-table is, the population standard deviation. Okay, it's 1.96. And if we could actually see this, you would see that at like 100, I think it's 1.98. Right? It gets very close to our standard deviation. It gets very close to what we would use if we knew what sigma was. Okay, so close that we're going to talk about that in a second. But these are the numbers I would have to use. So in our sample size was 25. So what value of T for a 95% confidence interval are we going to use? Anyone want to hazard a guess? Guys online can type it in. What am I going to use for a sample size of 25? 24, right? What is the value that we're going to use for T? Bingo, 2.064. Okay, why are we using the t-table instead of the z-table? We're using the t-table instead of the z-table because we don't know the population standard deviation. We've only been given the sample standard deviation instead of the population standard deviation. That's why we're doing this. Okay, and a sample is a sample, right? You've got to have a certain number of people. Now, technically, let me ask you something. If I took a sample of size 100 and I forgot this, that gee, I don't know the population standard deviation, and I used the z-score instead of the t-score by mistake, would I be off by much? No, it's only 1.98 versus 1.96. What's the big deal, right? Wouldn't be off by much. That's why you'll often hear in the text, it'll be mentioned, in other courses it'll be mentioned, that's why when you take a very large sample, say a sample of 100 or bigger, a lot of times you will see the textbook or whatever reference you're using, you'll see them use 1.96 instead of going to the t-table. Because they say to themselves, the sample's so big that I'm just going to use 1.96 instead of using the t-score. Okay, but by all rights, if you want to be 100, if you want to be as accurate as you possibly can, you would use the t-table all of the time. Even if it was a population of 1 million people and you sampled 999,999 people and there's one person left, and the t-value for that, if they had a table for it, was going to be 1.9600001. Technically, you should use that instead of 1.96, right? Because you still don't know, unless you sample everybody, you still don't know the standard deviation, the sigma for sure. Technically, if you have a piece of software, when you do it in person, if we took a sample size 100, I would be fine. If I gave you this on a test and I asked you to calculate confidence interval and I told you the sample size was 100, I would be perfectly happy to make the range have enough wiggle room in it. You know, I can tell you, in other words, if I ask you what's the lower range on confidence interval and it's 96, I can set on Blackboard how much of an error to put in there. In other words, I can say whether it's 96 and it will accept 89.9 and up to 91.1, 90.1. I can wiggle, I have that wiggle room. I'd be perfectly happy making it wide enough that it would give you a right answer if you chose to use the z-score 1.96 or the t-score 1.98, because the sample size is so big and because the t-value for that sample size is so close to the z-value. However, if you were a computer and a piece of software on a computer where it's just as easy for you to have every value calculated to 87 decimal places and you have every table built into you and so on and so forth. For instance, if you're SPSS and you calculate the confidence interval, it never uses the z-table. It always uses the t-value. Even if the t-value is 1.9601, it's always going to use the t-table because it can. Just as easy for it to use the t-value. For you, it's a convenience to not have to go to the table if the sample size is very large. Are you wrong if you use the t-table for sample size 100? No, in fact, you're more right, than using the z-value. But that's where you use it. You use the t-table where you don't know that, where I haven't given you, or this problem or the situation hasn't given you the standard deviation for the population. And you have to depend on the sample to approximate it. Okay, so let's go back to our example here. So in our example, let's calculate our confidence interval. Now our 95% confidence interval is going to be x bar plus or minus, and I'm going to put t over here. I'm going to put t for alpha is equal to 0.05, right, for 95% certainty. And then I'm going to put the standard error, plus or minus standard error. So that's 100 plus or minus the t-value for a sample size of 25 was what? Anybody remember? 2.064, good memory, times the standard error, which is equal to, it happens to be the same this time, right? Could have been different because the standard deviation might not have matched the standard sigma exactly, right? But I didn't want to spend all week doing this calculation. So it's equal to 2. So it's equal to 2. So now 100 plus or minus 4.132. So what's our confidence interval now? Our confidence interval now is on the high side 104.132, and on the low end is going to be 868. That look right? Okay, if I hit that, oh, I'm sorry, it's one. I'm doing it from 100. 95. I think that's right? If I add 132 to this, it's going to be 96, right? 2 carried 1, 7 carried 1, 868, right? So I got it right. It's a rare situation here where I do math in my head now. I've forgotten how to do math in my head since I got a phone. Okay, so at any rate, that's our confidence interval now. Notice something. All of these numbers are the same. Mean is 100. Standard deviation is 10. Sample size is 25. Standard error is equal to 2. And when I knew sigma, they're all the same numbers as knowing sigma and not knowing sigma. What's the difference here? My confidence interval It was 96.08 to 103.92. And now it's 95 something to 104 something. It's wider than it was before. It's wider because the t-value is bigger, and that I made to accommodate the extra uncertainty because we didn't know what sigma was. Okay? If the sample size were smaller, would this be wider or narrower? Would be wider. Why would it be wider? It would be wider because the t-value that we would use for a smaller sample size would be a bigger number from that table and make the margin of error bigger. So we're going to add and subtract a bigger number. Okay. Is everybody comfortable with that? Yes? No? Okay. So the t-score that I use here, right? The difference between the width of the confidence interval when I knew sigma and the width of the confidence interval when I didn't know what sigma was, I had to use a population standard deviation to estimate it. The reason why it's wider is because we use t instead of z. We use the t-value instead of 1.96. So the t-value is always bigger than 1.96, right? It's always going to be bigger unless you sample the entire population, which means that you're in this situation, you don't sigma, right? So the t-value is going to be bigger. So since the margin of error, the amount that you add and subtract from your sample mean, is going to be bigger than 1.96, then your interval is going to be wider because you're subtracting and adding a bigger number. And the smaller the sample size is, the bigger t is. So if sample size were 10, t might be 3. So 3 times 2 would be 6. So you're adding and subtracting a bigger number. So as the sample size goes down, t goes up, gives you a wider confidence interval. Makes sense. Smaller sample size, less confidence. You got to make your interval wider so that you can still say you're 95% sure. And as the sample size goes up, then our t-value goes down, gets closer and closer to 1.96, to the point where if a sample size is 200, a lot of times we don't even bother, we'll just use 1.96 instead of going to the t-table. But you're never wrong if you use a t-table. Good. So I think we kind of have this worked out a little bit, right? You guys okay with that? Okay. So I'm going to take this opportunity to talk about the other thing that we calculate confidence intervals for, and that's for proportions. How are you guys doing online? I don't see any chatting going on here. Yeah, I can't tell which of these are you guys, and if we have anybody online at all. So just so you know, I can't tell where if they're here or there. I can only see the list of participants. Okay, so let me get a fresh sheet of paper here. The other situation where we're called upon to calculate confidence intervals. Okay, blank sheet of paper. The other place where we're called on to calculate confidence intervals is for proportions. P's, proportions. Okay, so let's talk about what we do there. So where might that come up? We got election coming up here, so it might be a good time to maybe pick on that. Let's say that there is a proposition. Proposition 1A is on the ballot, and Proposition 1A is for whether or not strawberry smoothies should be legal in New York City. We had something close to that before, right? Remember we had that thing with the Slurpees and the limit on the size of sugary drinks and stuff like that. I don't remember. Was that a proposition? Did that actually make it to the election and it was proposition, or was the city council reject that or something? I don't think it ever made it as far past the city council. But at any rate, so we had an issue similar to this, except it was a real one with size of sugary drinks. Well, let's say we want to outlaw. We found out that growing strawberries contributes to the greenhouse gases, right? For whatever reason. and we want to outlaw strawberry flavored drinks. So strawberries, and we poll the population. So there are 9 million nowadays. The population of New York is really high now, right? Used to be for a while there in the 70s when we had no money and we were uh, uh, we got into a lot of trouble fiscally in New York City. I think it went down to 7.5 million or something like that. But now I think we're back up over 9 million. So it's gone up quite a bit in the last 30 years or 40 years. So 9 million people, this is really too many. That's really what this boils down to, too many people. So we don't have the resources to go around and sample 9 million people to get an idea of whether this proposition, the strawberry industry is fighting this thing. So they're deciding how much should we spend on advertising, right? They have, there's a PAC, it's the Strawberry Growers Association PAC, wants to know whether it should spend money on advertising in New York City to get this defeated. So they're not going to go out and they want to see, well, is this going to get shot down? Does this have a chance of passing? So they want to know what proportion of New Yorkers are going to vote yes to this. Are going to approve this. So what proportion equals yes, right? So we can't go out and sample all 9 million people, or maybe they're only interested in the 2 million and actually turn up, the vote, or that will have vote on the don't get to that page. A lot of people don't vote on the propositions that do vote, in elections. So maybe they figure there's 2 million people actually going to vote on this, right? They're not going to go out and and survey 2 million people, but they might say, let's do a telephone survey and let's sample 1,000 people. We'll hire 10 really hard up public health students that really need the money, right? And we'll tell them we'll pay them $15 an hour to make phone calls. 10 of them they only have to make 100 calls each over a couple of days, and we'll pay them for a couple of days. And they're going to call up 1,000 people randomly and ask them, are you in favor of this proposition, right? So it turns out that out of the 1,000 people that they survey, 475 people, let me make that a round number, 450 people tell them that they are going to vote yes. Okay, so P is population proportion of all New Yorkers that's going to vote yes. We don't know what that is. We're never going to know what that is. Actually, we will know what that is in this case. We're going to know it after Election Day, but by then it's too late anyway. So we don't know what the true population proportion that are in favor of this right now, right? But we do know that 450 over 1,000 people say they plan on voting yes. So our proportion of our sample, remember we used X bar when we were talking about a sample before? Well, now our proportion of our sample is going to be called Pcap, right? So Pcap, the proportion of our 1,000 people that we actually sampled, 450 said they were going to vote yes out of 1,000 that we're surveying. So our sample proportion is 45% are going to vote yes. So right now, the strawberry growers are feeling pretty good about themselves, right? And they're saying, this is not going to pass. Right? But however, maybe we should spend some money on this. Let's figure out, are we 95% certain that this proposition is going to fail, right? What do we know about the true proportion of New Yorkers? Maybe we underestimated it in this sample. Well, they want to know a confidence interval just as we want to know a confidence interval, right? So we're going to take a look at this. We're going to say to ourselves, I need to predict what the true proportion is given what I know here. And what do I know here? I know the population proportion, and I know the sample size is 1,000. Okay. Well, we've learned that there's a couple of formulas that we can use here. We can calculate our confidence interval by Pcap plus or minus, and I'm going to use 1.96 here, times our standard error. The variability, if I took samples over and over again of 1,000 people, what it would be like, how I would expect it to be distributed based on what this proportion is. Proportion gives us the variability too, right? So why did I use 1.96 instead of going to the t-table? Big sample, right? very large sample. Almost always, when you're working with proportions, you're going to be working with large samples, right? Because it's just a yes or a no. It's a one or a two, right? So with proportions, you're almost dealing with large samples. The other rule is that if you have a large sample, like 1,000 people that you use it, you have to have both sides of the outcome be greater than 15, right? In other words, even though it's a large sample, if we get 10 people that say yes, 990 that say no, right? Even though we have a sample size of 1,000, both sides have to be greater than 15. Thus, they use this qualification, use this excuse for using the z-score 1.96. Okay. So, well, what would the t-value be in this case? What's our sample size? 1,000. Yeah, it's one. So it's going to be 1.9607, right? So the answer to your question is, yeah, no, you wouldn't be wrong, but right, the answer is going to come out almost the same anyway. With this, both sides being greater than 15, right? So you literally, with proportions, you could argue use 30, right? It's a lot. Anything over 30 is a large sample. But usually, in practice, you're really dealing with these kinds of samples, hundreds, thousands of people that are being surveyed, like a political survey, right? Those are usually pretty big. They do a lot of calls. They ask a lot of people. So in this case, 1,000 might be typical, right? But you got to be careful when you say 1,000. If you get something that has very low frequency on one side, then things get a little dicey in terms of confidence interval, right? So if you stick to that rule, that you can use 1.96. And, and be honest with you, I would probably call 100 a large sample here, but both sides being over 15, right? In other words, if you had sample 100 people, it's got to be at least a 1585 split. Can't be a 1486 split. So let's call it 100, right? Is a large sample, but you're always going to be a large sample. So it's going to be equal to Pcap plus or minus 1.96 times the standard error. And how do I calculate standard error? I'm not going to go into the probability and how this formula came about, but it's equal to this. It's equal to P times 1 minus P over the sample size, right? Okay, now notice I use P, not Pcap. So by all rights, the standard error should be based on the population proportion, but you don't know that. So the only thing you have that you can use is Pcap, right? And how do we justify that? Same reason as before, we're only working with large samples when we're working with proportions. So what is the standard error? So we're statisticians. We can find an excuse for doing anything almost, right? So it's equal to the square root of 0.45 times 0.85 over the sample size of 1,000. Okay, so I'm going to calculate that. Excuse me, 0.65, 0.55, 0.55. I got that because I was still thinking of 15 from the last thing I was talking about. I have 15 stuck in my head because of the sample size. Okay, so let's take a look at this. I'm going to clear that. Thank you for catching that early before I actually did the calculation. Most students, they wait for me to get a half hour into a calculation and then they tell me I'm wrong, right? So I appreciate it when you stop me while I'm still a little wrong rather than a big wrong. So at any rate, 0.55 times 0.55 equals 0.2, about a quarter, right? That makes sense, right? 0.5 times 0.5 is about 0.25, so it's pretty close. I'm going to put that into memory because I'm going to need it in a second. Actually, I could have just divided by 1,000. Divided by 1,000 is equal to 0.00024. That seems like a very small number, except the fact we're going to have to take the square root of that number. And when you have a small fraction, take square root, it makes it a bigger number. Just like when you have a fraction, like say 0.2 times 0.2, it becomes 0.04. It becomes a smaller number, works the opposite direction. When I take my square root, that becomes 0.0157. I'm going to call that 0.016 for our purposes. If you're doing this on a test, I would keep the extra digit there, 157, right? But for now, or even keep the whole, if you're using Excel, you could even keep the whole number, or just put this into memory so that you can call it back again without even losing any of these digits. I like using Excel because it always stores all of the digits, and you don't have to worry about typing them in. So okay, so 0.156 for our purposes, I'm going to do this by hand. I'm sorry, 0.16 to make it easy for me. 0.016. Okay, so my standard error is equal to 0.016. It's really it was really 157 something, whatever it came out to. So that's my standard error. So let's do our calculation. 0.45 plus or minus 1.96 times 0.016. Okay, so 0.01, as I just mentioned to you, if I go back here, I already have this here, so I can multiply that by 1.96. So they come in handy after all. And that's 3%, it's roughly 3%, right? So my confidence interval is going to be 0.45 plus or minus 0.03, 3%. 1.96 is roughly 3%. So what does that come out? My 95% confidence interval is 0.48 on the high end and 0.42 on the low end. I'm 95% sure the true population proportion for New Yorkers voting on this proposition is going to be between 42% and 48% yes. What does that tell you about this proposition? Save your money, put it into strawberry futures because it looks like it's going to go down, right? And if you know this, you can go to the stock market, buy strawberry futures, make a lot of money tomorrow, or next Wednesday, right, after the election. So, and if you're in the strawberry industry, you say, let's save our money. We don't need the advertising because the 95% sure this is going to fail. If I wanted, I could have been 99. I could have said 99. If I wanted to be 99% certain, what would I have had to use instead of 1.96? 2.58, exactly. 2.58 times 0.16. Let's see what happens there. Oops. What's that? The interval showing is the 95% confidence interval for the true proportion of people that plan to vote yes in the whole population. Exactly, because you need 50% to pass, right? You need more than 50% to pass, right? In other words, 50% is outside of the confidence interval. Now let's see if I want to be 99% certain. What would it be if I want to be 99% certain? Well, let's see. It was 1.6 here. 1.6 here. 1.6, or let me do it as a percentage. 0.016 times 2.558 comes out to be about 4.1%. So 4.1% added and subtracted from 45 is about 49%. So it still looks like it's going to fail, even in 99% confidence interval. So the idea here is, what if it had turned out that our confidence interval had been 0.44 to 0.52? We're 95% certain that the true P, proportion of people that are going to vote yes, are between 40, the actual value that we had was halfway in between this, 6, 8, was 0.48 was our Pcap. And our confidence interval turned out to be 44.44 to 0.52. What could you say about the proposition now? Can you say with 95% certainty that it's going to fail? No, because 50% is within our confidence interval. It could be more than 50%, even at 95% level of confidence. So it's interesting. By looking to see whether or not a value is within the confidence interval, you can predict whether it's going to be different than the true mean or true proportion. Okay, so if it's outside the confidence interval, you can say you're 95% sure that the outcome is going to be different. If it's inside the confidence interval, you can't say that that's not the true mean or population proportion. So that's why the confidence interval is very powerful. It allows you to do things like, say, get rid of that. It allows you to, say, do a study and say you want to compare the total cholesterol for people who eat more than 5 servings of fruit. And you want to compare that to the total cholesterol for people who eat less than 2 servings of fruit, right? And you find that the average total cholesterol for, excuse me, let me put it this way. I mean, this is let's say that this is the entire population. Okay, and the population happens to be, population that you're looking at happens to be, where would they test everybody's cholesterol? Nursing homes in New York City. Nursing homes in New York City. And as it happens, nursing homes in New York City, they may test everybody's cholesterol in the nursing home, right? That might be a standard test they run. So you can actually find out what the average mu is for the entire population of nursing home patients. And mu could be, excuse me, 180. Let's say. Now you might want to go back and take a sample of that population, right? But only the people that are eating 5 servings of fruit or more in that population, and you take a sample size of 100, right? And you find out that in that sample, take a sample size of 100 or 200, which is pretty big, and you say to yourself, okay, I'm going to find my confidence interval for only the people that eat 5 more servings of fruit. That might be 10,000 people in nursing homes, but your sample's only 200. So you don't know what mu, here you know what mu is. Here you're working with X bar. So since you calculate X bar is equal to 160, well, gee, it looks like it's less than 180. I could say that, based on that, I'm encouraged. Sounds like people eat a lot of fruit in nursing homes that they have lower total cholesterol. But I don't know mu for this population. I only know X bar. So I need to calculate a confidence interval. And my confidence interval, if my confidence interval turns out to be, 160 is in the middle, if my confidence interval turns out to be 150 to 170, we're 95% sure the true mean for fruit eaters is 150 to 170. We're 95% sure that the true mean is between these two numbers. We're 95% sure it's different than 180 because 180 is outside of this confidence interval. We're 95% sure that this group is between 150 and 170, but we know this group is 180. So we can say that they're different with 95% certainty. Okay? What if I had said that this was 130 to 190? Are we still 95% sure that the two are different? Because this is inside of the confidence interval. It could be 180, right? Our sample size is not big enough for us to get a narrow enough confidence interval to be able to say that there isn't more than a 5% chance that they could have the same mean. Right? So the confidence interval gives us an enormous amount of power with regard to that, with regard to comparing two groups. Group where we know the mean, group where we don't know the mean, where we're at calculate the average. Now you could argue, let's say that I want to take this another step further. Okay, let's say that step is, I think there's another step further, and I'm going to say to myself, I want to compare whether the total cholesterol for French people, Frenchmen, Frenchmen, is different than the total cholesterol for Americans. Yeah, kind of a silly study, but French food is full of butter and all kinds of oils and all kinds of nasty stuff. right? And yet there's also the issues with Mediterranean diet, different kinds of oils, and so they're not Italians. They don't, it's not an olive oil thing with them. They eat a lot of butter, a lot of cream, and stuff like that. But they still have pretty low cholesterol. But they drink a lot of wine, and that's a vasodilator, whatever. So cardiovascular disease rates tend to be better in France than they are in America. But there's so many confounding factors. We're only looking at total cholesterol right now. Do Frenchmen have a different total cholesterol than Americans? We're not going to test every Frenchman and every American cholesterol. We're going to take a sample. So we're going to take a random sample of 1,000 Frenchmen and a random sample of 1,000 Americans. We don't know either. We're never going to know the true mean cholesterol for Frenchmen or for Americans because we're not going to sample every American, every Frenchman, right? So all we know is X bar from our study for Frenchmen and X bar for Americans for a total cholesterol study. Since we need to know how accurately we know the real means to compare these two, I'm going to do confidence intervals for them. Let's say the mean for Frenchmen is 160, and our confidence interval is 140 to 180. And for Americans, our mean was 180, right? And our confidence interval was 160 to 200. Can I say that these two are definitely different with 95% certainty? Right? The two confidence intervals, they overlap. Right? So if it turns out that Frenchmen are here and Americans are here, they might have the same cholesterol level. Right? We can't really say that they're definitely different with that level of certainty. We can never say anything in statistics definitely. That's why you always hear about confidence intervals and alpha error and so on and so forth that we're going to be talking about. Well, now, how about if I got a different result that based on that sample, I was able to say 160 and 180. However, it's a big enough sample and there's small enough variability that maybe that it turned out to be 155 to 165 was our confidence interval for Frenchmen. And for Americans, it was 175 to 185. We're 95% true that the true population mean for Frenchmen between 155 and 165, and for Americans, it's between 175 and 185. Now, can you say with 95% certainty that the true mean total cholesterol for Frenchmen is different than the true mean? Now it seems like you could say that, right? Because the confidence intervals don't overlap. You want to know something? In statistics, it's not unusual or improper to use what we did with the single sample. There is one sample versus a known mean. In other words, this was our confidence interval, and we were comparing it to a known mean to see if it was inside the confidence interval. That's okay, But in practice, we do not do this with confidence intervals. We do something else. We do something called a t-test that we're going to be discussing. It's kind of like this, but it's not exactly the same. There are technical reasons why we don't do this. A variety of reasons have to do with different variability in the two groups and errors that could be introduced by doing this. But we do something called a t-test. And a single sample, this is a single sample, right? We're comparing the mean we know to a single sample. This thing is a test that involves two samples, then one group to another group based on two samples. One group sample, another group sample. So we're going to talk about a t-test. But before we do that, we're going to take a break because I think I filled your head with enough stuff right now that you need like maybe a sip of something sugary or coffee or a break. Okay, so let's take a 5 or 10 minute break at this point. Anybody have any questions before we abandon this for a moment? Right, makes sense, right? Everything we've done so far kind of makes sense at this stage. You get the idea why we use a z-score sometimes and use a t. You see how we calculate confidence intervals when we knew sigma or when we didn't know sigma, and we work with proportions, and you figured out now. Now we should have that down, I think, pretty well now. So now we're going to introduce a new test and called a t-test, and we're also going to talk about something called hypothesis testing. Okay, let's take a break. That means, get up, walk around, open the door, let some air in here. because I need a break too. Okay, so you guys online, if there are any people online, I can't tell because nobody's typing into the chat box. I'm going to pause the recording and I'll start it again when we come back.
This conference will now be
Okay, so for you
recorded.
guys that are at home, if there are any of you there, we are back on and we are going to start recording again. You know what we should do? If someone, hey guys, if someone has a piece of paper and a pen, could you pass around an attendance sheet? Because I need to start taking attendance for the nutrition students, or they're gonna hang me at the end of the semester. Okay, so yeah, we got somebody doing it up here, so don't worry about it back there. But yeah, pass it around. Make sure everybody signs the attendance sheet, please. Okay, so we're recording again. We got screen back up, I think. Yes, we do. And so I'm gonna go ahead with this. Yeah, just put the date and PH750. Okay, and name. All right, so let's think about this for a second now. If I have a population, like remember those Frenchmen we were talking about, total cholesterol in the Frenchmen and total cholesterol in Americans, right? Those are two populations, right? I don't know what mu is for either one of them, Americans and Frenchmen. But let's say somewhere in the background, there's someone that knows what the true mean of these, true mean and standard deviation for each of these two groups is. There's someone hiding out there. And it turns out that for Frenchmen, it's the mean is 160 with a standard deviation of 10. And for Americans, it's a mean of 160, 180 with a standard deviation. No, let's say standard deviation is also 10, for argument's sake. If I were to draw normal distributions for these two populations, these are the actual distributions for the populations. If I knew this, for let's say this is 150, this is 140, 150, 160, 170, 180, 190, okay, 200, okay. Now we know, hang on a second here, the mean of the entire population for Frenchmen is 160, the mean for the entire population of Americans is 180. We know the means are different. We don't have to do a statistical study. If we actually knew that, we would just say, hey, the average Frenchman has the better total cholesterol than the average American. But we don't always know that, right? We don't ever know that usually, right? We base everything we do on samples. I'm just going to draw what the populations look like. Okay, so 160 is here, and two standard deviations below would represent 95% of Frenchmen. So that'd be 140 to 160, 180. So the average population of Frenchmen would look something like that. And what's the average population of Americans? Well, it'd be 180, but 20% below, two standard deviations below would be 160, two above would be that. So the average Americans are going to look like this. There's a lot of overlap between the two populations. There are Americans that have lower cholesterol than some Frenchmen. Some Frenchmen have higher cholesterol than some Americans. These two populations overlap, right? So if I were to take samples of size 1,000, really big samples here, and I drew now I didn't draw the population distribution. I drew the sample, the means for repeated samples, means for the samples, X bars for the samples. And if I took them over and over and over again with a sample size, big sample size, like 100, a big sample size stuff, right? Right. Well, what would these samples look like? These samples from this population. Well, if we took them over and over and over again, they'd have the same mean as the population, right? As the two populations. So the average for Frenchmen would be here. The average for Americans would be here. But now, because I'm taking samples and it's a big samples, the distributions are going to be narrower. So the distribution of all the samples is going to be like this for Frenchmen and for this for Americans. Well, occasionally, if I take a sample of 100 people, I might get one that's, and 100 people that are Frenchmen, I might have some bad luck. and get some Frenchmen and get a sample of 100 Frenchmen and find that it turns out, my sample turns out to be, let's say 170, 170, let's say 100, 170, let's say. And I might get some Americans and take a sample of 100. I might get unlucky and get a sample mean of 170 also. I might not notice there's the difference between the two means for the populations because my samples happen to be too high for the Frenchmen, too low for the Americans. So I have to make sure that when I take my samples, that my two X bars are far enough apart that I can say with 95% certainty, they represent two means that are really different. And I'm going to do that using something called the t-test. Okay, what does a t-test consist of? The t-test consists of measuring how far apart the means of these two populations are. Okay, so let's say I take a sample from one population, from the Frenchmen, and the average for that one is 162, pretty close. And the average for the Americans is 158. Are they far enough, 108, 178, right? Because the average was really, the true mean, which is hidden from us, was really 108, 178. Are they far enough apart for me to say with 95% certainty that the real mean for Frenchmen does not equal the real mean for Americans? That's my problem. That's what I have to solve. I need to, since I do, I'm going to do studies like this all the time. I'm going to take one group, find its mean, the mean of my sample. I'm going to take a second group, find the mean of that sample. And I'm going to want to be able to say whether or not these two populations have different means. Where might I use this? If I give a blood pressure drug, I want to be able to prove that the average blood pressure for people who take the drug is different than the average blood pressure who take a placebo. I want to be able to, and I can only do that from a sample because I don't know the real, I'm not going to test every person that ever takes the drug. If I want to know whether an intervention, a public health intervention, like training nurses in recognizing serious asthma cases, whether or not they catch more asthma cases or don't catch more, I want to compare the performance of nurses that were trained versus nurses that were not trained. And again, that's a sample that I'm going to be doing, not every nurse everywhere, right? So I'm always going to be stuck here trying to decide whether the mean of group 1 is equal to the mean of group 2 or they're different than each other, right? They're two different population means. Notice I'm always talking about population means. Even though I'm only working with means of samples, it's really the population that I'm interested in. So this is what I'm really interested in doing. I'm interested in starting off saying that the two groups are equal, that means they're equal, but now I want to prove that, gee, they're different, right? So I am starting here with the intention of getting to the point where I can say this with a certain level of certainty. We call this a hypothesis. Our hypothesis is that the two means are equal to each other. The mean total cholesterol for Americans equal to the mean total cholesterol for Frenchmen. And I want to gather enough evidence to be able to say that indeed that they're different. We always start from this point. We start from that point and we call that the null hypothesis. We always start from the point that the two means, two proportions of the two groups are equal. And we attempt to prove the alternative hypothesis. What's the alternative hypothesis? That the two means are different. Okay, we're going to talk later on about single-tailed, two-tailed, single-sided, two-sided, and so on and so forth. But for now, this is enough. We just want to prove that they're different. Not that the Frenchmen are higher or lower. We're not going to prejudge this in terms of who's higher, who's lower. We're just going to see the results. So in order to prove this, what do I have to do? I have to get enough evidence to prove that this is not true. So now we can say with a certain level of confidence that this is true. Okay, so that means I have to reject the idea that they're equal. I have to have the evidence to reject it, that they're equal, and accept the alternative that they're not equal. So I have to disprove this in order to accept this. Okay, that's called rejecting the null hypothesis. This is called accepting the alternative hypothesis. In order to accept the alternative hypothesis, I have to reject the null hypothesis. I always start with the equality. Right? So how am I going to prove that? Well, I have to prove that with a certain level of certainty. So up to this point, what's the standard kind of level of acceptable percent of certainty that we've been working with? That's not a hard question, right? 95%. So 95% certainty implies that you're willing to accept up to 5% chance of being wrong. From now on, we're going to call that our alpha error, right? If you want to be 95% certain, you're willing to be 5% willing to have 5% chance of being wrong, right? If you want to be 99% certain, that means that your level of acceptability for error is only 1%, right? Alpha is equal to 1%. We're going to use that term alpha to represent the level of type 1. This is called type 1 or alpha error. Okay, and right now for this session, I'm avoiding going into this whole discussion of alpha and beta error and power and so on and so forth. We're going to leave that for a future session. I just want to introduce this concept of how we're going to prove with 90 or demonstrate or attempt to prove with 95% certainty that we can reject this idea and accept this idea. Well, we already saw that what we need to do is to make sure that the mean of our sample for Frenchmen is different than the mean of our sample for Americans, that there's a big enough difference between the two of them, right? Well, big enough difference is relative. If there's a lot of variability in the numbers for cholesterol, right? In other words, some people have very low levels, very high levels. So enormous variability. We're less certain that X bar tells us what is close to the true population mean. X bar 1 and X bar 2 are close to their individual true population means. So if there's a lot of variability, these two numbers have to be further and further apart for us to be 95% certain. If there's very little variability, like Frenchman's cholesterols are from our sample turn out to be 159, 160, 157, 162, and Americans turn out to be 180, 179, 182, and so on. If that's the kind of variability that we're seeing, well, the X bar 1 and X bar 2 don't have to be very far apart for us to have a high level of confidence that the means are really different. On the other hand, if the variability was 160, 120, 205, if the variability within each one of these two samples is big, then our confidence that our mean X bar represents our true population mean in both of them is shaken a bit, right? So now we need them to be further apart. So another way of saying this is that if we have really, really big samples, we want these two means, right? These two sample means, they're really, really big sample sizes. We want these two means to be at least 2 standard deviations apart. Technically 1.96 standard deviations apart. Because if they're 1.96 standard deviations apart, remember everything relates back to our distribution, our central limit theorem of distribution. That suggests that there's less than 5% chance they could have come from the same population or populations with the same meaning, right? So we want them to be far enough apart that we can say that if we take a really big sample size, that we want to be sure with that number of standard deviations apart or standard errors, because we're dealing with samples, that distance apart, to be able to say that we are 95% sure that the means are different, right? Well, let's say it's not a giant. Let's say the sample size is not 1,000. Let's say the sample size is 25, right? Well, now 25, now we got this extra uncertainty about our variability and so on and so forth. So instead of using 1.96 to justify saying that these are far enough apart, we're going to use the t-score for size 25. So instead of having to be 1.96 apart, now they have to be 2.064 standard errors apart. If the sample size is 10, now they have to be 3.75 standard errors apart in order for me to be 95% sure. Why? Because as the small sample size gets smaller, my level of uncertainty goes up. So I am going to use that t-score in place of z to predict whether or not I can say with a certain level of certainty that these two means are different. Okay, I'm going to start now by using a single sample p-test. Okay, because single sample is going to make things a little bit simpler for us. And as we get into this, I'm going to give you some basic rules, basic steps in hypothesis testing. Because that's what we're doing here. We're testing those two hypotheses. First of all, well, what are our assumptions here? What are our assumptions here? Our assumptions here are that the samples are random for each population. That every individual in population A has the same chance of being picked with the same probability. In population B, every individual has the same probability of being selected. That they're random, truly random samples. Also, if it's a small sample, that the population, the two populations are approximately normally distributed. As the sample size gets bigger and bigger, that's less important, because we know the central limit theorem says as the sample size gets big, then we don't have to worry quite so much about them being perfectly normal, right? But for small samples, that they're approximately normal, right? And we need to know what the sample size is, because that's going to impact all of this thing. Okay, so how do we start here? We start by stating the hypothesis, null and alternative. Why do we do that first? We do that first because we don't want to go through a calculation and then say, oh, well, you know, what we're really looking for is what we round up to. You want to state your hypothesis first and then go through the exercise of proving it or failing to prove it, right? So you state it first. So I'm going to give you an example. Oh, how did I do that? What happened there? My goodness. I don't know what happened there. I touched the trackpad. Oh my God. Don't tell me I can't undo that. Okay, let me quit this. Oh boy, I should be able to rotate this. Let me open it up in preview. Should be able to rotate this now. Oh, thank God. I feel myself sitting here trying to read this sideways. Let me minimize this. Okay, so our first task is to state the null and alternative hypothesis. I'm going to give you an example. And it's going to be a single sample t-test in this case. I'm going to tell you that the average blood pressure for Great Danes, dogs, Great Danes. I have no idea what dogs' blood pressures are. Average blood pressure for Great Danes for all Great Danes is equal to 100. And I want to compare the average blood pressure. This was done in an exhaustive study of thousands of Great Danes and so on and so forth. The surveys of all vets all over the country. So we happen to know what the true mean is for Great Danes. And then I'm going to compare that to the average blood pressure for Chihuahuas. If I spell it right, average blood pressure for Chihuahuas. And I don't know what mu is. I have no idea what it is. I'm not going to be able to find out. So I'm going to have to work with a sample of Chihuahuas. So I go out to a vet and I find 25, I randomly sample 25 Chihuahuas. My sample size is 25. I find that X bar, my mean for Chihuahuas, turns out to be 140. They're nervous little dogs, right? This could be higher, who knows, right? So, and my standard deviation turns out to be, standard deviation turns out to be, I'm going to call it 20. Okay, So now I need to figure out what my confidence interval is for, one way for me to do is figure out my confidence interval for chihuahuas. And what's that going to be? It's going to be X bar plus or minus the t-value for a sample size of 25, right? For 5 alpha is equal to 0.05 or 95% certainty, right? T-value times my standard error. What's my standard error? My standard error is equal to sigma. I don't know sigma, so I have to use standard deviation. Oh, and that's also why I'm using t instead of sig. 20 over the square root of 25, which is 5, and that's my standard error is equal to 4. So what's my confidence interval? It's going to be 140 plus or minus t, which is for 25, 2.064, or 2.06, times 4, right? So what does that turn out to be? That turns out to be 140 plus or minus my margin of error, which is 4.12. So that's going to be, I'm gonna round it off to 136 to 144. So let's say, well, if the Great Danes were 100, say 120, they were 120, it's outside of our confidence interval. I can say with 95% certainty that the mean for Great Danes is different than the means for Chihuahua. Well, how about if I said that the Great Danes were 137? Well, now I can't be 95% certain that the Chihuahuas are not 137. It's within my confidence interval, right? So I can't say with 95% certainty, with less than a 5% chance of being wrong, that the means of these two, the true means of these two dogs are different. Yes. Oh, I'm sorry. Yeah, 8. Thank you. 8.12. Right. So it's 132. I'm gonna round it to 132 and 148. Okay, but still, that 137 is inside that confidence interval. So I can't say that they're different. I'm going to do this a little bit differently, though. I'm going to say to myself, well, how many standard errors, instead of taking my t-score and calculating a confidence interval, I'm going to calculate how many, what is T and Z? T and Z are the number of standard deviation things that are apart, right? Number of standard errors, in the case of Z, it's, right, in either case, it's the number of standard errors or standard deviations. The two measurements are apart. So I'm going to take the mean of 137, and I'm going to compare it to the mean for the Chihuahuas, which was 140. So 140 minus 137, the difference between them is 3, right? And I'm going to divide that by the standard error for the Chihuahuas. What was the standard error for Chihuahuas? It was 4, right? So how many standard errors are these apart? These are 3 over 4. They're 0.75 standard errors apart. In other words, they're 0.75 standard errors, the t-values, the number of t's apart, or z's apart that they are, is 0.75. Okay? Let's change this now. Let's say this turned out to be 120 instead of 137. Well, now, 140 minus 120, okay? How many standard errors apart are these? The number of standard errors apart that they are now, let's see, 140 minus 120 is 20 divided by 4. They're 5 standard errors apart. Right? So, in one case, the number of standard errors apart is 0.75. In the other case, the t is equal to 5 standard deviations apart. Well, what does that mean to us? That means that these are so far apart that the likelihood that they came from the same population is tiny, right? If the sample size were 1,000, so we could use n instead. If this value were bigger than 1.96, we would say that they're far enough apart that we can say that these two means came from different populations, that the two means of the populations are different, and we can reject our null hypothesis. Well, since the sample size was small, it was only 25, that critical value that we have to exceed is no longer 1.96. What do you think that critical value is that you have to exceed? Might be. What does T have to be, T critical? That you have to be more than that number of standard errors apart. What's the sample size? 25. Where would I get the critical value of T? You might have even noticed it on the table. They refer to those numbers as T critical. In other words, they have to be 2.064 standard errors apart. So I'm gonna make these numbers a little bit more practical if I can. Okay, I'm not going to try and identify these as a specific group or thing. I'm just going to say that we know one group, group one, we got group one, and we have group two. Two different samples from two different populations. This one we know the mean. The mean is equal to 100. This one we take a sample of size 30, right? And we find that X bar is equal to, let's call it 110. And let's say our standard deviation is equal to, let me think about this for a second. Standard deviation, the variability of the individuals in that sample, right? Or in other words, our estimate of sigma is going to be 10, divided by, I'm thinking of a good number for us. Is equal to 5. Let's say standard deviation is equal to 20, for argument's sake. Okay, so I want to compare the two of these, right? So I know that the mean for this first group is 100. And we know the mean for this group is 110. And the standard deviation is 20. But the variability that we would expect with a sample of size 30 from this group with a standard deviation of 20 is going to be determined by the standard error. And the standard error is going to be equal to 20 over the square root of 30. Let's calculate that. Oops, I lost it somewhere. Okay, clear. 30, square root of 30 is 5.5. I'm going to put that into memory. Okay, and I'm going to divide 20 by the square root of 30. And that comes out to be 3.65. So our standard error is equal to 3.65. Okay, so now, how many standard errors apart is 100 from 110? And how do I calculate that? Well, that's the number of t-scores. Number of standard errors is the t-score. T is equal to 100 minus 110 over the standard error, which is equal to 3.65. Before I calculate this, for this size sample, how large does T critical have to be for me to reject the idea that they're equal and say that they're far enough apart, 100 and 110, to say that they come from populations with different means? What does T critical have to be for a sample size of 30? Let's take a look. Sample size of 30 is 29 degrees of freedom. It has to be 2.045. So T critical, oops, let me get that back. So T critical has to be equal to or bigger than 2.045. So let's calculate T critical. What is T critical? Where my calculator go? There it is. Oh, it's behind this. I can't see it. You can probably see it. I can't. It's behind this thing. Okay, so let's clear this out. So it's going to be 10 divided by 3.65. So what is our t-value? Our t-value is 2.73. 2.73. Okay, the amount that these have to be apart for me to say that the two populations have different means is RT critical. Are they far enough apart for us to say that? Yes, they are. Our t-value for the distance between these two is 2.73 standard errors apart, which means that they're far enough apart that we exceeded our critical value to be 95% certain that the two means are far enough apart. So if I exceed my critical value of t, what can I say about these two populations? I can say that they have different means. Let's formalize this now. Let's actually take this and formalize it. What's the first thing that we had to do? What was rule number one? We had to state our null hypothesis alternative. So what is our null hypothesis here? Mu1 is equal to mu1. The mean for group 1 is equal to mean for group 2. That's H null hypothesis. Well, it's our alternative hypothesis. Mu1 is different than the mean for group 2. H alt. Right? Okay, so what's the next thing we had to do? Let's find that sheet again. Number 2, specify a level of significance, a level of error that you're willing to accept. Okay. Now, before we used to turn that as confidence. We used to say 95% sure is good enough, right? Well, being 95% chance of being right is the same thing as 5% of being wrong. So instead of stating as being 95% confident, we're going to say that our level of significance, the level at which we're willing to say that they're different, is if the level of error, chance of our being wrong, is less than 5%. So we're going to, instead of saying 95%, we're going to say alpha is equal to, our tolerance for error is equal to 5%. These are equivalent, aren't they? 95% chance of being right, same thing as 5% chance of being wrong, right? So alpha is equal to 0.05. We have to state that. What's the next thing we have to do? Draw a sample of size n, compute the test statistic, okay, use the z distribution when sigma is known, use the t distribution when you have to estimate it from the sample standard deviation, okay, and then determine the p-value. Well, 4 and 5, we're gonna wait a little bit on that. Instead of doing 4 and 5, we're gonna say, look up the critical value of t that you need for that sample size, and if your critical value of t is exceeded by the difference between the two means, the number of standard errors apart that the two means are, you can reject your null hypothesis. So you say, go back and say, I reject the null hypothesis that the two means are equal, and I accept the alternative hypothesis that they are different. In this case, we could say that they're different. But let's say that instead of group 1 being 100, group 1 was equal to 105. Right? That would be 5 over 3.65. Our calculation for t would be 5 divided by 3.65. How many t values, how many standard errors apart are they? Well, approximately 1.4. I'm going to call it 1.4. This comes out to be 1.4 now. Now, can I reject my null hypothesis? No, because I haven't exceeded the critical value of t for me to have 95% certainty, less than 5% chance of being wrong. If I were to say the two means are different, two population means are different. I could do this another way too. I could actually calculate a probability of being wrong. Okay, and I'm not going to do it here because in order to do it, we would have to have a large sample size so that we could justify using the z table instead of the t table. So I'm going to leave it at that for now. Okay, and what I'm going to do next is I am going to open a sample. Okay, if you can't find one, put this up. Okay, we're going to do an example. The mean SAT score for a population of first-year students at Hunter is 620. The standard deviation of scores in this population is known to be 95. We know sigma. An investigator believes that the mean SAT score of first-year psychology majors is significantly different from the mean score of the population. The mean of a sample of 36 randomly selected first-year psych majors is 648. State the null and alternative hypotheses. Okay, I'll take this one. I'm going to say that the mean for all first-year students is equal to the mean for psych students. And my alternative hypothesis is the mean for all students is not equal to the mean for psych students. Okay, so now I have to calculate my standard error. What do I know here? Well, actually, let me put down what I know here first. I know that the mean for all students is equal to 620. I know what mu is, right? And I know X bar for psychology majors is equal to 648. Okay, why did I use X bar? Why did I use mu for everybody and X bar for the psych students? Yeah, one of them they told me what the true mean was. The other one, my only clue is the sample. Now, I don't know what the true mean is for all psych students, right? So do I know what sigma is here? Well, I do. I was told, right? I was told the population standard deviation is 95. I know what sigma is here. So that means I can work with the Z table instead of the T table. Okay, that's another way I can work with the Z table for probabilities. I can also say that T critical is going to be equal to what if I know what sigma is. I can work with the Z table. So what is T critical for 95% or 5% chance of being wrong on the Z table? It's equal to 1.96. If I didn't know what sigma was, I would have to use a T table and look up T critical for sample size of 36. But I know what it is here, so I can use 1.96. Okay, so now I'm going to calculate my standard error. What is my standard error equal to? It's equal to sigma over the square root of the sample size. Sample size is 36, so it's divided by 6 is equal to sigma 95 divided by 6. And what does that turn out to be? It turns out to be 6 is 30, 31 and 2/3, 0.67. Okay. Tell me if I'm wrong. I think I'm right. Okay. So now calculate what is the appropriate test statistic? We already did that, right? We said that T critical or Z has to be is 1.96. And we're going to calculate what T actually is. What is T for the difference between these two means? It's equal to 648 minus, doesn't matter which one you put first because we're just looking at the size, absolute size of that number. 648 minus 620 over 31.67. Yes. I did it wrong again. Huh? 15.86. Oh, you're right. Yeah, look at that. 15 point. Oh, I did 3 into that, didn't I? Instead of 6 into that. 6, 1, 35, 15. 15, that leaves 35, 5, 6. Is that? 6 is 1, leaves 35. 6 into 35 is 5, and 0.67? 0.83? Oh, yeah, because it's a 6. 0.83. Okay, not a third. For some reason I was thinking of 3. Okay, so 15.83. So let's see what this is. Divided by, I'm going to call it 6. I'm going to call it 15, might as well use 15.83. So how many standard errors apart are these? What is the T value that we wind up with? 20 over 15.83 equal to 1 point. Anyone to give me the numbers? 1.0? 1.7. Okay, 1. Okay, 1.8. Okay, so have we exceeded T critical? Are they far enough apart for us to say that they're different? No, we haven't, right? So let's go back up to our null hypothesis. What are our conclusions here? Our conclusion is we fail to reject the null hypothesis. Have we proved that the two means are the same? No, we haven't. All we've done is fail to prove that they're different. So we never say that we accept the null hypothesis in this situation. What we say instead is that we fail to reject the null hypothesis. Well, let's say that instead of being 648 and 620, that the mean for these students turned out to be 668 instead. Well, how would that be affected here? Well, X bar is 668. 668. Well, this is going to be 668 minus 620 is 48, right? 48. 48 over 15.83. And my t-score now is 3.03. Well, what are my conclusions now? Do I reject my null hypothesis? My t-score is 3.08. Is my null hypothesis bigger than my critical value of t? Is 3.03 bigger than t? It is. So I can reject my null hypothesis. Now, the reason why I use 1.96, and you guys remember why I use 1.96? Because we were given the standard deviation of the population. We were given sigma. So I use 1.96. If I wasn't given that and said the standard deviation of our sample, scores of our sample is 95, well then I couldn't use 1.96. T critical, the value I have to exceed, now has to be the T value that I need for 95% certainty for a sample size of 36. Or in other words, a sample size, a number of degrees of freedom of 35. Let's go get that. 35 degrees of freedom. We don't actually have that, so we're going to be in between these two. I'm going to be conservative and say 30, and that would be 2.04. Okay, so our critical value is going to be 2.04. In this case, did it change any of our conclusions? No. Right? The first case we would still fail to reject. Second case we would have still rejected. But there's a little bit in between there where it might have come up where because we didn't know the population standard deviation, it might have caused us to fail to reject null hypothesis. Okay. So I'm going to give you guys a question. I'm going to let you guys do one. Okay. I don't like that one. Let me find a better. Whoops. Oh, thank you. I don't like this one either. Let me find a better question. I'll just put one. I'll just make one up on the fly. Okay. Okay. The blood lead level for children in New York City. In New York City. Oh, I got a better one. Let's do this. The blood lead level for children in Flint, Michigan. In Flint, Michigan, from you know, in a lot of older cities with older plumbing and so on and so forth, it's not unusual for them to monitor blood lead levels in children almost universally, test all the children In other words, require, in addition to vaccination, require tests for blood lead levels when they're going into first or second grade or something like that, like 5 or 6 years old. So that's not unusual. So it's possible that we may know that the blood lead level for all children, the mean blood lead level for all children in Flint, Michigan, between 2012 and 2014 was 3.1 micrograms per deciliter. That's usually the unit that they use for blood lead levels. Now you are a physician, a pediatrician in Flint, Michigan, and you think, I've been seeing a lot of children lately with elevated blood lead levels. I'm going to do a little study. I'm going to randomly sample 25 students in Flint, and I am going to measure their blood lead level. And it turns out that in my study, the mean blood lead level is equal to 5.1. And the standard deviation for my readings is roughly, let's say it's equal to, the standard deviation is equal to 1.2. Okay. I want to see if I can prove that blood lead levels currently in Flint, Michigan, the true mean blood lead level now in 2018 for children in Flint, Michigan is different than it was in 2014. Okay? So you got a given mean that you're going to compare it to, and you got a sample that you took. So you're comparing a known mean versus a sample. That's a single sample t-test. You're going to calculate the value of t for this calculation. Okay, so go through the 5 steps, except the first 3 of the 5 steps, right? Because we're not going to do t. We're not going to do p, that probability. Go through the 5 steps here. Number 1, state your hypotheses. Hypotheses. Number 2, state your level of significance. In other words, what level of error are you willing to accept? And number 3, do your t-test, single sample t-test. So I'm going to give you a few minutes to do that. Okay. I'll give you another minute or two. Yeah, go through it systematically. Okie doke. I'm gonna go through this. Okay. Anybody want to tell me what my null hypothesis is? What's my null hypothesis here? Mu for the for 2014, blood level, the average blood level of 2014 is equal to mu for 2018. Notice I use mu in both cases. I only know X bar. But when I form my hypothesis, I'm concerned about the population means, not the sample means, because it really is all about the population means. Sample means just a method to get to this. What's my alternative? Mu for 2014, new blood levels for 2014, does not equal U for 2018. That's my null hypothesis and my alternative hypothesis. So I've stated them. What state the level of significance or the accuracy that you want this with? What's your level of significance going to be? How are you going to describe it? Alpha equals, what do you think? 0.05? Okay. So now I have to calculate whether or not these two means, the mean I know, and the mean I'm approximating, are far enough apart for me to be 95% sure that the populations that they came from, the means of the populations they came from, mu1 and mu2, are really different. And how do I do that? I do that by determining the number of standard errors apart that they are. In other words, the t-value that they are apart. Well, before I calculate t, I have to figure out, well, what t do I have to exceed? What is t critical? What's the t-value that I have to exceed to be 5%, have less than 5% chance of being wrong when I reject the null hypothesis, given that my sample size is equal to 25? What does that t-value have to be? I'm going to wait for somebody to tell me. What do you think that t-value has to be? Somebody must know. Hang on a second. It would have been 1.96 if we knew sigma, the standard deviation, right? But since we only have a sample size 25, it's going to be the number we get from the t-table for that sample size, right? Which is going to be 2 point how much? 2.064. That's what we have to exceed to reject the null hypothesis. What would it have been if the sample size were 10? What would it have been? How much? What? Huh? That's going to be different. T-score is going to be different based on sample size. How many degrees of freedom is 10? 9. So on the table, what is the T critical going to be from the table? Right. Look up the T table. Tell me what is T critical for 9 degrees of freedom, for 95% confidence or 5% chance of being wrong. Same deal. Somebody must know. You guys got the T-table up? Somebody got the T-table up? No, that it's got smaller size, so it's going to be a bigger number. Okay. In other words, look at the T-table, look for 9 degrees of freedom, and go over to the column for 95%. Same thing as 5% chance of being wrong. 2.3, what was that? A little louder. 3.3, that sounds right to me, right? If the sample size were only 5, what would it be? 2.77. So notice, as you get a smaller and smaller sample, it gets harder and harder to reject the null hypothesis because you have to exceed a bigger T critical value. And that's that middle column, that 95% on that T table. So let's calculate what our T value actually is. And what is our T value equal to? It's equal to mu minus X bar over the standard error. Okay, so what was mu? What's the mean that we know? 3.1. And what's the mean that we don't know that we have to use the average for is 5.1, right? Over the standard error. So we have a standard deviation of 12 and a sample size of 25. So what is our standard error equal to? It's equal to 12 divided by the square root of 25. So what is the standard error? It's 12 divided by 5, right? Is 2.4, right? I'm sorry, it's 1.2. It's 1.2. It's 1.2. It's 0.24. 0.24, right? Okay, so my standard error is 0.24. So I'm going to divide 0.24 into the difference between these two means. So it comes out to 2.0 divided by 0.24, and T turns out to be roughly 8. Okay, what was T critical? 2.064. Have I exceeded T critical? I have. These are 8 standard deviations apart, standard errors apart. That, it's an enormous amount given the variability, right? So I go back to my null hypothesis after I've run my t-test. So since I've exceeded T critical, these are far enough apart for me to be able to say they're different with less than 5% chance of being wrong. What can I say about my null hypothesis? What can I do with my null hypothesis? I can reject my null hypothesis and accept my alternative hypothesis. You have just proved that Flint, Michigan it's lead poisoning the children, because in 2014, before they went to a new water supply, the average blood lead level for children was only 3.1, and now it's significantly higher with less than 5% chance of being wrong, right? So that's literally what a pediatrician did in Flint, Michigan. She recognized that she was getting suddenly getting higher average levels of blood lead than she had been previously in previous years. Yes. We didn't choose 1.96 because it was a small sample size. And we didn't know sigma for the population. We only know the standard deviation for the sample, right? In order to use 1.96, we have to know the standard deviation for the entire population, or it has to be a very large sample size, say 100. 100 or bigger, right? Bigger than 100. Okay, then we would use 1.96. Okay. That's why we didn't use the T critical. We didn't say T critical was 1.96. We looked it up on the T table for that specific sample size. We actually could have, even if it was 100, the sample size, we could have looked it up on the table. And if you go to that table, mine's messed up for some reason. It's not displaying correctly. If yours displays correctly, if you go down to the bottom where it says 100 degrees of freedom, the critical value of T is 1.98. Right? So it's not quite 1.96. So you would have to exceed 1.98, not 1.96. But it's so close that chances are if you're going to exceed 1.98, you're going 1.96, you're also going to exceed 1.98. Right? Okay. So What if we're doing this with SPSS? I have an example here, and I'm almost done, I promise. And I will release you from this torture. I have a sample here. Of 9 people. And the average value here, the mean for this sample, is 10. Okay, roughly 10. It's actually a little bit different. I have these rounded off, I guess, to 0 decimal places. Actually, I should change that format cells. Come on. Number. Okay. It's actually, oh, it is exactly 10. That's my mean. That's X bar for my sample. And my standard deviation for my sample is equal to 2.74, a little under 3. So now this represents my test group. And I'm comparing this to a known population. And the mean mu for the known population is equal to, I'm going to call it 9 is going to be equal to 9. Right? The average mean, the mean for the known population is 9. My test group, I know X bar. I don't know the true mean for the test population. I say it's equal to 10, right? So I want to compare 10 and 9 to see if I can really say that these two groups have different means. Okay, so how do I do this? Well, first I need to calculate my standard error. You know, in order to do that, I need my sample size. My sample size is 9, right? Sampled 9 people. My standard error is equal to my standard deviation divided by the square root of my sample size, which is 3. My standard error is 0.91. So now I have to calculate my t-score. How different are these two values, 10 and 9? Well, the way I calculate that is going to be the difference between the two means, right, which is 10 minus 9, and I'm going to divide that by the standard error. Oops. And I get a t-score of 1.09. Okay. Well, I know right away I can't say that they're different, because what's the smallest t-critical I could possibly have if I had a giant sample size? 1.96, right? So what is t-critical anyway for sample size of 9? Anybody want to tell me what t-critical is for a sample size of 9? 2 point, how much? 306? Okay. So I would have had to exceed the t-critical in order to say that the true mean for test group 1, the test group, is different than the known population that I'm comparing it to, where I know the mean in that population, single sample t-test. Okay, well, what if the difference had been, what if the known population was 7 instead of 9? Well, then my t-score was 3.28. Did I exceed my t-critical? Well, they're far enough apart that I could say with about 95% certainty, less than 5% chance of being wrong, that they're different. So I can reject my null hypothesis, accept my alternative hypothesis. I'm going to open up the same file in SPSS. That's going to be the last thing we're doing today. Same file in SPSS. Eventually, it will open. Okay, these are the same numbers I was working with before. Right? I'm going to go in there. I'm going to go into Analyze, and we're going to start to use SPSS quite a bit more as we move forward, because we want to get into you being able to do real statistics when you go into other courses. I'm going to go into Descriptive Statistics, and I'm going to ask SPSS to take this variable, X, that I called it, and tell me what the mean is and the standard deviation is. I'm going to click Continue and click OK. Oh, actually, I could have done something. The output window is going to come up, and the mean is 10, and the standard deviation is 2.739, just as we saw before. Sample size is 9. I actually could ask it for a little bit more. Descriptive statistics, descriptives. I'm going to go in here. I could have asked it for the standard error, as well. I'll do it again. Okay, and it calculated standard error just as we calculated ourselves manually. Gave us the same numbers. Now, I'm going to actually do a test, ask it to do the t calculation for us. Analyze. Is there anywhere here where I can compare means? Well, boom, compare means under analyze. And I'm going to go over here, and what kind of test do I want to compare means? One sample t-test. Independent sample t-test means two groups. Paired samples means another thing. ANOVA means another thing. But only thing I'm interested in, right? So I'm only have a single sample. I'm comparing it to a known mean. So that's called a one sample t-test. So in here, which test variable am I comparing? I want to find the mean of this group X. And what am I going to compare it to? I'm going to compare it to the number, I'm going to say 7.5. Let's say the population mean was 7.5. Okay? And I'm going to click OK. I could have put in 9 and we know it would have failed. I could put in 7 and we know it would have been successful. I'm going to put in 7.5. I'll click OK, and it compares those two means, divides them by the standard error, figures out a t-score. What is the t-score? The t-score is 2.739. For a sample size of 25, what did we say t-critical was? T-critical was 2.3 or something like that, right? Did we exceed t-critical? Yes, we did, right? 8 degrees of freedom, yes, we did exceed t-critical. So this t-score says we can reject the null hypothesis. But look, SPSS goes further than that. They go over here and they tell me two-tailed significance. They tell me that these two means are so far apart that if I look at a normal distribution, they're so far out that the two tails at either end, at the extremes at either end where they're separated, the two tails add up. See, because there's two-tail significance, two-tail, they add up to 2.6%, right? 0.026. That's my probability of being wrong if I reject the null hypothesis. So not only did it give me the t-test that I compare my t-critical, when I do that, I only know there's less than 5% chance of being wrong. But it actually, to SPSS, actually tells me what the exact probability of being wrong is. And it tells me the probability that you're wrong if you reject the null hypothesis is 2.6%. What was my acceptable level of error? Alpha? 5%. What is my actual level of error? Only 2.5% if I reject the null hypothesis. So I can reject the null hypothesis and know that my chances of being wrong are less than what I said is my limit, 5%.